Did you guys have a good weekend? Some nods. I got a verbal. Someone had a good weekend. It's good. Where did I put my? Oh, they're right there. Does anyone have no midterms this semester, this week? Someone has no midterms. Someone else. Nice. After 5 last week, you're down to 0 or something. So, good. Well, let's get started. Who'd like to offer a prayer for us? Anyone? Anyone? Thank you.
Dear Heavenly Father, we're very grateful to be able to be here today from we're very grateful for the story and all the creation of this class. Please bless today that we will be able to learn and be able to appreciate what we are taught and that we will be able to apply it. We're very grateful for all those things, and we say these things in the name of Jesus Christ. Amen.
Amen. Thank you. How about comments about the forum today? It was good. People could probably say that even if they didn't go. It was good. Yep. Any particular comments? Can someone that went, explain what it was about to those that didn't go? Go ahead.
It's basically the guy who was giving it was a leader of it, like an interfaith coalition kind of thing. He was talking about like interfaith cooperation and diversity and that kind of stuff. It had a lot of very good ideas, and it was very good.
Yeah, really talking about drawing strength from others' religions, ideas, how he's done that. He talked about having a really good friend that was LDS growing up. How faith groups getting together caused some big changes. It was important in helping Nelson Mandela get out of prison, for example. But the last part was really about as you start to work with, as you go out and you're volunteering and serving and working, you're going to be interacting with people of other faith. How much do you know about their faith? You might be willing to share about yours. Are you willing to ask about others? So that was a big part of it. And he had lots of examples that had impacted him and had impacted history. In the 1 o'clock class, we actually have a student that is Muslim from Jerusalem. So you don't have to go far away to have opportunities to talk to people about that. Yes, Ryan? No, I didn't. I need a haircut, but my hair gets long enough that I have to start pulling it back out of my eyes. So it's just gelled back a little bit. So, but thanks for noticing, I think. One of my good friends, she used to teach math education here at BYU in the College of Education. She was a teacher educator. She was Baptist. She worked here for 20 years. She commuted from Kentucky. Her husband did not want to move to Utah, and he stayed in Kentucky. And she would fly out for 2 weeks, go home. Go home. She'd try to get if she could, she'd try to get all of her teaching in one semester, so she could spend more time at home. But very different. Just loved Christ, and I learned a lot from her. She retired about 3 or 4 years ago. We just published a paper. We got a paper published together 3 months ago or so. I strongly encourage all of you to get on speeches.byu.edu and listen to a devotional given by Boyd K. Packer and his Muslim friend. He brought a Muslim friend. He let the Muslim friends take most of the time. And they talked about the similarities between their religion. Boyd K. Packer says, I sat down with my standard works, and he sat down with his Quran, and we talked about things. And It's fantastic, fantastic, especially it was given at a time when there weren't really high regard towards Muslims. I was getting emails at the time from a friend that was kind of bashing Muslims, and I sent that link to him to listen to, and I never got another bad one email again about Muslims. So yes. I don't, but if you search for Boyd K. Packer in the speeches.byu.edu, it's probably about 10 years ago. So, okay. Let's pull up, oops, I don't know why that's showing that one. Okay. So here's a problem. Here's some problems. Take a few minutes to work on these problems. Number 3 was up from last time that we never got to talk about. I'm going to talk about it. I'm going to start by talking about it. But if you don't get to it, that's fine. I think some of you already got to it and have thought about it. But Porter, can you turn your phone off, please? Gosh, I can't believe you did that. You're welcome to talk with a neighbor, compare answers, raise your hand if you've got a question. Just take one more minute or so. Okay. The problem in 3 is we have a matrix. We have 2 matrices. One represents your protein, fat, and carbs in terms of peanut butter, bread, and jam. One represents your protein, fat, and carbs in terms of milk, oatmeal, and sugar. And we're given a vector in protein, bread, and jam. So this vector, this 1, 1, 1 means you have one serving of peanut butter, one serving of jam, one serving of bread. Okay, but we want to know what that is in milk, oatmeal, and sugar. First, how would you figure out what your protein, bread, and jam vector is in protein, fat, and carbs? What could we do if I have this 1, 1, 1 in peanut butter, bread, and jam? I think I misspoke and called the protein, bread, and jam ones, but peanut butter, bread, and jam. How can I get that into protein, fat, and carbs? Augment the protein matrix, augment the P matrix with 1, 1, 1, and then get the answer. That would give us the vector that we could multiply by the protein, the P vector, to get 1, 1, 1. So that would actually tell us how to, what vector is in peanut butter, bread, and jam. If we wanted, that would be equivalent to 1, 1, 1 in protein, fat, and carbs. So, so that's not what we need to do here. That's more complex than what we need to do. So, you raising your hand? We just need to multiply the P vector by the servings. So, because this multiplication represents 1 times 8, 15, 7, plus 1 times 4, 1, 8, plus 1 times 0, 0, 13. And if this is servings of, if these are all peanut butter, things associated with peanut butter, the nutrition facts associated with bread, nutrition facts associated with a serving of, bread and jam, and this is one serving of this, one serving of this, one serving of this, then what am I going to end up with? I'm going to end up with however much in protein, fat, and carbs. So if this is a peanut butter, bread, and jam vector, then multiplication changes it. It's the same information, it's just represented in a different coordinate system, coordinates with a different basis. So I'm going to get a new vector over here that's protein, fat, and carbs. Okay, that's the easy part. If I want to go with, the whole thing is to go to protein. Gosh, I shouldn't have picked 2 P's. Oh. Peanut butter, bread, and jam to milk, oatmeal, sugar. I'm going to use protein, fat, and carbs to be my in-between, because that's an easy thing for me to do. I can at least go here to protein, fat, and carbs. And now I have a new matrix that if I multiply this matrix by servings of milk, oatmeal, and sugar, then I'm also going to get what? Protein, fat, and carbs. So these matrices, both of these matrices, give me servings of their foods and put me into protein, fat, and carbs. But the problem is, I already have something in protein, fat, and carbs now, and I need to go to milk, oatmeal, and sugar. Use the inverse. That's right. So I can take my protein, peanut butter, and jam, multiply it, I get protein, fat, and peanut butter, bread, and jam. Multiply it by by P, I get protein, fat, and carbs. But now I want to translate this into milk, oatmeal, and sugar. I need to multiply by the inverse of this, because this will take milk, oat, meal, and sugar and transfer it to to protein, fat, and carbs. I need to go back the other way. So I need to take M, multiply it by my protein, M inverse, multiply it by my protein, fat, and carbs, and that will give me the equivalent in milk, oatmeal, and sugar. Ryan? Yes, so yeah, so you can do things. This is exactly where your first comment comes in. Yeah, here we don't know, we're trying to figure out what do we multiply by. So another way to think about it is what do we multiply here to get our desired protein, fat, and carbs, and then you can augment and go, which is equivalent to finding the inverse matrix. So, yes. Yes. If you're doing it, if you have a particular one, yes. But we're actually going to use this inverse thinking to come up with an important formula in a little bit. So not today, but give us a few days. So to generalize, if I have V in peanut butter, bread, and jam, I can multiply it by P, which is my peanut butter, bread, and jam, and then multiply that by M inverse, which was my matrix with the connected milk, oatmeal, sugar, and protein, fat, and carbs. And that is going to get me the equivalent V in milk, oatmeal, and sugar. So like this is one nice thing here already. If you can think about it as an inverse, we can just write it down here. And these multiplied together will get me just one matrix that I can multiply. If you give me peanut butter, bread, and jam, I could just multiply it by this one matrix, and it would give me directly my milk, oatmeal, and sugar coordinates. So this is one advantage of thinking in terms of matrices here, because you can think about it more generally, what's happening. Okay, questions about this? Okay. All right, let's go to number 1. Show this transformation T is a linear transformation. What you have to do is show that something is linear, a transformation is linear. Ryan? What's the definition of a linear transformation? Yes? Okay, so here's one criteria. So that's our first criteria is the transformation of a sum of two vectors has to be the sum of the transformation of the two vectors. Okay, and next? Okay, and if we transform a scalar multiple of a vector, that needs to be the same. We need to end up in the same place as taking the scalar multiple of the transformation of that vector. Okay, so this is kind of algebraically, or property-wise, this is what it means to be linear. We already talked intuitively. A linear transformation is anything that takes a line to a line and the origin is fixed. Those are the transformations we're talking about. Okay, so how do we show, so from the definition, if we can show that both of these hold, then it's linear. So I already have the work for number 1 up here already. So some of you may have noticed that already. I just didn't want to erase it and then write it up again. I was so lazy. I hope you guys don't judge me for being lazy. Okay, so I wrote down U and V as those C's came in later for something else. Just to throw you off. I think I have another C somewhere too. Boom, okay. So I defined U to be x1, y1, z1, V to be x2, y2, z2. Why did I do x, y, and z? Why not just x, y? Why not x, y, z, and w? What? Someone was talking over here. Yeah, we have 3 different variables in our transformation. We're in our 3. So I put down three coordinates. Okay. And I'm going to start with this side, T of U plus V, and then I'm going to use our transformation and algebraic manipulation, and I'm going to try to end up with T of u plus T of v. Okay. Sometimes when you're writing proofs, it's nice to work backwards to help you make the connection, to figure out what's going in between. So if I know I want to end with this, it's nice to think about what comes before that. What am I trying to get to before that? How would I make that last step? And in this case, I'm going to start with, if I'm starting with x1, y1, z1, and x1, and x2, y2, z2 as my u's and v's, I probably want to get to the transformation of the x's, x, y's, and z's added together. Okay? So this helps me to know what I might want to shoot for as I do the transformation, as I do the manipulation. So T of u plus v, I add my u and my v, and I write it as my transformation here. And now each one of these, I have 3 cells, and my transformation says I take my thing in my first cell, I subtract it, and add 2 times the thing in the second cell. That's what my first coordinate, my new x coordinate will be. My new y coordinate will be the thing in the second cell. Subtract the thing in the second cell minus 5 times the thing in the third cell. Okay, that's going to be my new y coordinate. And my new z coordinate is going to be the thing in the third cell, or my old z coordinate, and change the sign. So that's what I do right here. I just plug these in wherever they go in my transformation. So my new x, I get a negative x. So that whole thing is my old x, plus 2y, that whole thing is my old y, minus y, so that whole thing again, minus 5z, there's my old z, and minus z. Okay, so I wrote that out. And if I want to separate these things, then it'd be nice to do some manipulation so I can actually keep all my x1s, y1s, z1s, and my x2s, y2s, z2s separately, so I can write them as separate things. Okay, so that's what I start shooting for. So I distribute out and I start grouping all the ones with all the sub 1s over here and all the sub 2s over there. Each line is still equivalent. It's mathematically equivalent. I just distributed and separated out. And then I took this side, wrote it as one vector, took this side, wrote it as another vector, added them up, and then recognize, hey, this is exactly the same as the transformation if I just have x1, y1, z1 as my input. And this is exactly the same as the transformation if I have x2, y2, z2 as my input. And that's the same as tu plus tv. Okay? Yes?
So in the book, they said that if you write it as a matrix, like that as a matrix transformation, that we could already prove that it's a linear transformation.
Yes, that's a slick way to do it.
If I wrote the matrix, how will I just finish its top saying doing the proof?
Okay.
Does that make sense?
Yeah, so here, we'll get to that because that's the next thing I'm going to do.
Okay.
So this proves 1/2. The other half is to do a similar thing, but instead of u's and v's, instead of x1, y1, z's, and x1, y1, z1, you're going to multiply by a constant. So then you take t of cu, and that's the same as t of cx1, cx2, cx3. Oh, I didn't do x's and x's. I did x, y1, z1. And that's the same as a negative cx1 plus 2cy1 minus minus cy1 minus 5cz1 minus cz1. Okay, and you just keep on going with a similar thing. You manipulate, you end up pulling a c out of everything until eventually you get to, that's the same as c times t of u. Okay, so it needs both of these. to prove it from the definition. Okay. So if it asks you, like one of your homework problems asks you to prove it from the definition. If it doesn't stipulate how to do it, then the best way to do it is to use the theorem in the book that says, hey, it's a linear transformation if and only if you can write the transformation as a product of matrices. So that's a really nice thing to know. And then so can we write this as a product of matrices? Can I transform this x, y, and z into this by just a matrix product? So this is a 3x1. Okay, this is a 3x1. Right, this looks, you might think like, hey, that's not 1. Look at how wide that is. But this is just one term, right? These are all added together. Those are just one cell. So what can I multiply here? What size does this need to be to multiply that and get this 3x1? A 3x3. I need to have 3 columns because I've got 3 variables here. I need a column with each variable. I need to end up with 3 rows. So I need to start with 3 rows. So if I think about the first row up here, what do I have to multiply by x by to get a negative x? Because that's what I end up with in the first row. -1. How about to end up with 2 y's? And how about to end up with 0 z's? 0. So the matrix we're going to end up with right here is just going to be the coefficients. 0, -1, -5, 0, 0, -1. Okay, so if you're writing this out as a proof, I'd say, I'm going to show that T is linear by showing that it is equivalent to a matrix product. So notice the transformation is equal to, and then write this out. And say, so by the theorem in the book, it is a linear, T is a linear transformation. Okay? That is a lot shorter. Yep. Yeah, theorems are nice. Theorems save you a lot of work. So learn theorems.
So there will be times where you can't find a matrix that'll be like a product of matrices.
Yeah, so like if I added 1 right here, then that's not equivalent to a product multiplication of a matrix. If we could put in adding matrices, then I could add a matrix after this. 0, 0, 0, 0, 0, 0, 0, 0, 1. Now those are the same, but this is a different kind of transformation. So this is a shifting, and we're considering linear transformations, those that keep lines to lines and keep the origin fixed. So that's one kind. If I squared z or cubed it or took the square root, that's going to be another situation where you can't just get that by multiplying this, because you can't get a z by linear combinations of x, y's, and z's. I mean, sorry, you can't get a z squared by linear combinations of x, y's, and z's. So this won't keep lines as lines. It'll change some to parabolas or something. And the algebra doesn't work out because you're going to end up with a squared, and then you're going to end up with this 2z1 z2 term, and that doesn't, you don't have that anywhere in here. You'll still have a z1 squared and a z2 squared, but that thing's going to throw you off. So algebra doesn't work out. Okay, we had a hand. Okay, great. If it shows you, go ahead.
So if we were to see that z squared, we have to go through all the algebra to show it. If we just figure out the fact that it
So the best way to show, pick an example to show. If they have you say, if they say show that this isn't linear, or show that this is, either show that it's linear or show that it's not linear, the easiest way to show that it's not linear is to just do it by example, okay? Because we don't have a theorem that says, oh, if there's a squared term in there, it's nonlinear, okay? Otherwise, you could use that theorem, but if you just pick like 111 and 222 and plugged it in, then you could show that, hey, t of 111 plus 222 is not the same as t of 111 plus t of 222. So, and that's all you need to do to show it's not linear. Or you can do this, you can do the C one, like pick 111 and let C equals 2, and you can show that t of 111 is not the same as 2 times t of 111 is not the same as t of 222. Okay, does that help? Yeah, the book does an example with those. Okay, other questions? Okay, let's do 2. So in the book and the video, it emphasizes one nice way to figure out the standard transformation matrix if you're given the transformations in words, like it rotates this way and it stretches this way. And that strategy is you only have to look at what happens to your standard basis vectors. So your transformation matrix, if I know what happens to E1, which is, oops. If I know what happens to 1, 0, this is only for a 2 by 2. If it was a 3 by 3 or whatever, then I'd look at 1, 1, 1, 1, 0, 0. I just have to look at what the transformation does to 1, 0, and then I'd put it here. And then I'd look to see what happens to, well, I should put this transformation of 0, 1, and I put it here. And that's a really easy way to figure out what your transformation matrix is. Easier than we were trying to figure out, well, if you have an arbitrary x, y, where does it go? What changes signs? How much does it move? You just have to focus on these elementary vector, these standard basis vectors. So let's do that. So here's 1, 0. Here's 0, 1. So we're going to rotate. So let's focus on this first one. We're going to rotate by 45 degrees. So it's 45 degrees. What are my new coordinates right here? Okay. It'd be negative 45, but yes. So you can do this, you can represent this in different ways. You could say that's going to be cosine of negative 45 degrees and sine of negative 45 degrees. We have to do negative because the standard rotation, we work this way, right? So we could write it this way. We could also write it as, if you do the geometry, this is 1, this is a 45, 45, 90. This is going to be the square root of 2 over 2, square root of 2 over 2. But this is down. So square root of 2 over 2, negative square root of 2 over 2. Okay? So I'm going to use this one. Okay? But both ways are great. So this is the coordinate of this point. But that's only after we do our first transformation. That does the rotation. But then what's the second transformation? It stretches in the y direction by a factor of 3. So I'm going to be off the board here, but it's going to stretch it down there. is the x coordinate is not going to change, right? They stay on this line, but the y coordinate, the new point's going to have 3 of these lengths down for the y coordinate. Okay, so I can multiply this by a -3, I mean by 3, and that goes to after times 3y, I don't know, then square root of 2 over 2, -3 times the square root of 2 over 2. That's this first basis vector, the standard basis vector, goes to that point. And the theorem says, hey, that is the first column of this transformation matrix. So you can just put it there. Okay, see if you guys can do the next one. Okay, think about where this goes when you rotate it 45 degrees and then stretch it by a factor of 3 in the y direction. So see if you can figure out this column here. So take a minute. Okay, let's go through this as a class. Where is when I rotate it, what are the coordinates going to be? Okay, so square root of 2 over 2, square root of 2 over 2. It's going to be those coordinates. Okay, or cosine of -45 degrees, sine of 45 degrees, whatever that is. Okay, and then that gets the rotation down, but now we have to stretch it in y by a factor of 3 in this direction. Again, my x coordinate isn't going to change. I'm going to stay on this line, but this distance, the new y coordinate will be 3 times this distance, but that distance is the square root of 2 over 2. So I'm going to be up there. So I'll have the square root of 2 over 2 and 3 times the square root of 2 over 2. Okay, and that is that is the second column of my transformation matrix. So the strategy here, start with your basis vectors, just figure out where your basis vectors go. Where they go is the new, those are your columns. So, okay, questions? So some of you may have tried another way. You can think about the transformation as a whole, a rotation counterclockwise of 45 degrees. Ends up being this. And stretching in the y direction by a factor of 3 is this. And if you multiply those together, you get this. Now, I couldn't have written this down like when I was in your shoes. You can learn the formula that they give in the book with the cosines and sines. And so you could just plug in any theta. So, but some students did that in the last class. My question is, can I switch these? In general, no. Some rotations, some transformations, it doesn't matter which order, but it matters here because if I stretch in the y direction first, So then this, it wouldn't change this basis vector, but my 0, 1 would become 0, 3. And then if I rotated by 45 degrees, I'm not here. I'm not up here. So I don't end up with the same thing. So how would I know I have to multiply in this order? It seems like you should multiply in the other order, right? I do the rotation, then the stretch. Yes? That's right. That's right. I mean, we read left to right here. It's easy for us to think, oh, we do the rotation, then the stretch, but the products go this way, right? I have to multiply by my point by the rotation first and do that transformation, and then by the result of that, I can multiply by this one, which does the stretching. So this is the order you need to do. Yes. Oh, that's right, like S of T of X, like that. Yeah, nice. So yeah, we did that one first and then the S. So, okay, very nice. Let me pull up a GeoGebra activity for us. Okay. So there's two equations, two linear equations right here at the very top. 2x minus 3y equals 11. A negative 3x minus y equals a negative 8. The solution is 7, 1, because that's where they intersect. Got one solution there. Okay. Another way to think about those equations is if we think about them as vectors, then you have x times the vector 2 and a negative 1 plus y times the vector negative 3, negative 1 equals the vector 11, negative 8. And the question is, what x and y values will equal 11 and negative 8? The geometric way of thinking about that is I have this u vector, that's the vector 2 and a negative 1, that corresponds with the coefficients of x. I have this v vector that corresponds with the vectors of the coefficients of y. And the question is, how many u's and how many v's do I need to get to the point 11, negative 8? And that's represented by a down here. So the answer, we already know the answer, it better be 7 u's and 1 v. So if you lined up 7 u's along there and then 1 v, you'd come back to a. I'm going to show what happens when you row reduce in terms of transformations. Okay. If we write this as a matrix, here's my coefficient matrix, and I start row reducing. I didn't augment it here. So what we'll do is we'll figure out what the row reduction is, and I'm just going to multiply the matrix by our row reduction matrix, and also the point by our row reduction matrix. So what's my first move? So here I have 2 and negative 3, minus 1 and 1. If I want this 2 to be a 1, what do I do? Divide by 2 on the first row. I could add both rows if I wanted to. Like there's more than one way to do this. I divided the first row by 2. So the matrix that I would use to do that is this one, 0.5, 0, 0, 1. And when I multiply those two together, I get 1, a negative 1.5, a minus 1, and a minus 1. Okay? Yes, Ryan? So you can see here it's M2 times M1. So yeah, so if I've got my original one here, I multiply that row reduction matrix, the matrix that's equivalent to row reduction on my left. And what happens is U goes to this vector, V goes to that vector, and A goes to that point. So what's the transformation that happened when I did that row reduction? I divided that first row by 2, but what, oh, so you said divide by x by 2. If you divided all the x coordinates of all the points in the plane by 2, then that's your new thing. We shrunk everything towards the y-axis by 2. So now W, how many, now the question is how many W's and how many A's does it take to get to D? It's the exact same. I have not changed, like the solution is still the same. Row reduction would work if that changed, but it stays the same. So I can get rid of my U's, my U and my V. Where'd my V go? It shouldn't be there. There we go. And I just have AVs, and I can even get rid of my A. So now the question is, yeah, how many W's and A's do I need? Well, let's continue our row reduction. I want to get rid of this -1, that lower left-hand one, and I could do that just by adding the 2 rows together. So I'm going to keep the first row, but add the 2 rows together to get my new second row. And the matrix that does that is this one that I've labeled M4. The 1, 0 across the top will keep my first row. The 1, 1 will add the 2 rows. And when I multiply M4 by my last matrix, I get this: 1, a -1.5, 0, a -2.5. And if I multiply that matrix by W, U, and D, it does a transformation, and that transformation is a shear transformation. It's going to take W, this line that's like on the line y equals a -x, and it's going to take that line and push it up so it becomes the new x-axis. Okay, so it's like I just have a quick picture here of here's Bart. Okay, so here's our friend Bart. So this is the original. When we do the transformation, it's going to push up, or you can think of it as pushing that x-axis up, so it's at an angle of 45 degrees. So that's the trend, and the other side comes down. So that's the shear transformation. So W gets pushed up to be B. A gets pushed down because it's on the other side, because we go like this. It gets pushed down to be C. And D gets pushed up to there. And now I can get rid of D, A, and W. And I can do the next transformation. So I want this -2.5 to be a 1. So I want to multiply that bottom row by a -1 over 2.5, which ends up being 0.4. So that's this matrix, M6. And if I multiply M6 times our last matrix, M5, I get 1, a -1.5, 0, 1. And when I multiply my vectors and my point toward times that one, well, so yeah, then I get, oops, my -1, 1, and B ends up staying the same. B ends up doesn't move anywhere. The point 1, 0 stayed 1, 0. So C goes to B, and what happens to G? It goes to that point. So where'd my G go? So now the question is, how many B's does it take and how many D's does it take to get to J? Same number. After one more transformation, we will have to do no work to know how many of those it would take. So let's do that last transformation. So I want to multiply, I'm going to multiply the bottom row by 1.5 and add it to the top row to get that -1.5 to be 0. So the M8 here, that's my transformation matrix. I multiply by M7 and I get our friend the identity matrix. And so my coordinates, my vectors are now just 1, 0, and 0, 1. So that D becomes, the D becomes that vector. B stays the same still. And J becomes this point. What is the point? Where did J get transformed to? 7, 1. Let me. So through those series of steps, we end up with a transformation that takes U and V, and they become our standard basis matrix vectors. And A goes to a point 7, 1. So how many of the first standard basis vectors does it take to get to line up with M? 7. And how many of the second one do we need to go up to get to M? 1. Because the coordinates of M, 7, 1, that's exactly what the coordinates mean. Well, it takes 7 of the first basis vector and 1 of the second basis vector to get there. So we do this transformation, so you end up with these nice basis vectors, and the solution then we can just read off as the coordinate of that point. Yes? Oh, where you do these transformations? No, I don't think so. No. Yeah, it would. Yeah, I've tried to solve, can I draw the vectors and just think about the transformations to figure out things? And it's not easier. It's rarely is it easier, I should say. So, yes. Oh, yes. Yeah, you may be asked to find, to write down as a matrix, what's the matrix equivalent of this row reduction? Yes, you may be able to do that. I think you had some homework problems where you did that. So, yes. Okay, have a great day.